Hello everyone. Welcome to the second session of Step to IoT, a webinar series on the Internet of Things organized by IET on campus, University of Peradeniya. In the last week's session, we talked about the definition of IoT, the basic concepts, and also the differences between IoT and the Internet, as well as machine-to-machine devices. Today, we are going to talk about a typical IoT architecture and its components, and also we are going to talk about IoT reference models. For those who are joining us today for the very first time, let me introduce the guest speakers of this event, Mr. Anuradha Udunuwara and Mr. Rajiv Weragama. Engineer Anuradha Udunuwara is a senior enterprise solutions architect at Sri Lanka Telecom with more than 17 years of experience in the industry. He graduated from the Faculty of Engineering of University of Peradeniya with a bachelor's degree in Electrical and Electronics Engineering. He is the world's first MEF Network expert with many other related achievements. Moving on to Mr. Rajiv Weragama, he is a senior engineer at Sri Lanka Telecom with more than 12 years of experience in the industry. He has a bachelor's degree as well as a master's degree in electrical and electronic engineering, and he's currently pursuing a PhD on the Internet of Things at the University of Peradeniya. Apart from being engineers at SLT, both of these individuals are researchers, trainers, as well as well-known speakers at Commonwealth telecommunication organizations. Now, without much more delay, I would like to invite Mr. Udunuwara and Mr. Weragama to start today's session.
Thank you, Sri, for your kind introduction. I hope all of you can see my screen.
Yes, sir.
Thank you. So good evening to all of you. Today is the second day of Step to IoT webinar series organized by the IET on campus at University of Peradeniya with the collaboration of IEEE Central Regional Subsection. So today we will discuss more on the typical IoT architecture and its components and also the IoT reference models. So there is a four-stage architecture in IoT systems, which is widely used and discussed around the world. So this stage one of this particular architecture consists of the sensors and actuators. The stage two represents gateway and data acquisition system. So we call it DAS. And next, in the third stage, we will see the edge IT systems, and finally, there will be the cloud. So the first two stages represent the operations technology. We call it the OT. And the last two stages represent the IT, we call the information technology. And first of all, we look at the stage one, which consists of sensors and actuators. The main difference between an actuator and a sensor is that the sensor converts the physical gesture into electrical signals and do different tasks. So on the other hand, an actuator is responsible for the conversion of electrical signal into a mechanical work. So these sensors can be temperature sensors, vibration, heart rate monitors, or whatever. They will collect the data from the environment or the so-called things which are under the measurement and will turn into these signals into useful data. So if we think about our smartphone, It is equipped with a gravity sensor, so we normally call it an accelerometer, which detects the directional pull of gravity and the phone's relative position to the Earth. And then it converts it into data that the phone can use to orient the device. So actuators can intervene to change the physical conditions that generate data. And for an example, it can shut off a power supply, and also it can adjust an airflow valve, or it can move a robotic gripper in an assembly process. And there are so many applications related to actuators as well. So sensing or actuating stage covers everything from legacy industrial devices to robotic camera systems, water level detectors, air quality sensors, and so on. The scope of the IoT is expanding rapidly thanks to several things happened in recent past, such as the development of low power wireless sensor network technologies, and also the power over Ethernet, or in other words, PoE. So PoE enables the devices in wired LAN to operate without the need of AC power sources. So there are different techniques which we can use for that. There's a particular standard defined by the IEEE 802.3. As I remember, it's a TOAF. So in 100 Mbps LAN, even though we find 4 pairs in the Cat5 cables, when we are dealing with speeds or the bandwidth around 100 Mbps, only 2 pairs are being used. So other 2 pairs of wires can be used to send power to the end devices. So in an IoT architecture, some data processing can occur in each of these 4 stages, at the stage 1, stage 2, or even at the stage 4. So it is possible to process data even at the level of the sensors and actuators. But there are so many limitations of resources at the level of sensors. So we have to choose between the immediacy and the depth of insight. The more immediate the need of the information, the closer to the end devices our processing needs to be. For deeper insights that require more extensive processing, and in that case, we have to send data to the other stages. So the stage 2 is internet gateways, or DAS, we call it the data acquisition systems. So data we collect from sensors are in the analog format, and the data acquisition systems, which are connected to these sensor networks, convert the analog data into digital signals. And it also performs the data aggregation. Data aggregation is a technique to combine data packets. So this has the potential to eliminate the meaningless or redundant data and can reduce the number of size of the transmission as well. As the large numbers of data is produced in stage 1, we need to deploy some kind of a high-speed gateways and networks to transfer this data to the other stages. Now let's see what sort of technologies which we can use for this data transmission. It spans from WPAN to WWAN. First, we'll discuss what is WPAN, or the Wireless Personal Area Network. So under this category, we'll find several low-range communication technologies, such as near-field communication, or NFC, Bluetooth, Zigbee, and IR. So these technologies can be used to replace the cables of the IoT peripheral devices. So the range will be about few meters. And that means these can be used within the reach of a single person. The next level is the wireless local area network, or WLAN. It can cover area about up to 100 meters, and IEEE 802.11, that is Wi-Fi standard, falls into this category. And also there is a competing standard developed by the ETSI, the European Telecommunications Standards Institute. We call it the Hyperland. That also falls under WLAN category. The next one is the WMAN, or the Wireless Metropolitan Area Network, which can cover a certain city, and the radius would be somewhere from 100 meters to few kilometers. And WiMAX falls into this category. And finally, we have the long range solutions. Now we call them as the cellular technologies. And there are so many cellular technologies, starting from 2G, 3G, 4G. 4G means LTE, LTE Advanced, LTE Advanced Pro, and now we have even 5G as well. So the copyrights of all these logos are with their respective bodies, and I use them here for the educational purposes only. Now the stage 3 is the edge IT systems. So once the IoT data has been digitized and aggregated, it is ready to cross into the realm of IT. However, the data may require further processing before it enters the data center, which are at the stage 4. This is where the edge IT systems come into the picture. So edge IT systems processing, edge IT processing systems may be located in a remote office or in other edge location, but generally these are located somewhere closer to the sensor networks, unlike the clouds. Because IoT data can easily eat up the network bandwidth, and also it can swamp your data center resources, it is best to have systems at the edge which are capable of performing some kind of an analytic part before moving into the cloud. So that will lessen the burden on core IT infrastructure. If you just had one large data pipe going towards your data center, which carries all the data collected by the sensor network, then we will need an enormous capacity in that pipe. So there will be a huge security concern, because since you are sending all those collected data within that particular pipe, if someone gets the full control of those of that pipe, then he will get the full authority of all that data, and your system might be in a high risk. And also there will be storage issues and delays in processing data as well. With the staged approach, we can pre-process the data and generate some kind of a meaningful result before sending that into the next level. So for an example, rather than passing the vibration data collected from the water pumps, we can aggregate and convert this data and analyze it and send only the projections as to when each device will fail or when will it need the next service. So there are several concepts related to these remote computing, and we call them mist, fog, and cloud. So Mixed computing is the extreme edge of a network, typically consisting of microcontrollers and sensors. So mixed computing uses these microcomputers and microcontrollers to feed into fog computing nodes and potentially onwards towards the centralized computing services located at the cloud. So like the mist you see in the morning, it is closer to the data collection point. Or in fact, sometimes these are embedded within the data collection device or within the sensors. So as the name suggests, this is the thinnest out of all. Mist is thinner than fog and fog is thinner than the cloud. So that means it's having the least computing power compared to the others. Fog is the next level, which is denser than the mist, but thinner than the cloud. That means it has more computing power than mist computing, but has a lesser ability compared to cloud. Cloud has the highest computing power and analytic capabilities out of all. So if you look at the numbers, there are millions of mixed computing devices, but you will find few hundreds of clouds. So the stage 4 is the data center or the cloud. So data that needs more in-depth processing and where the feedback does not be immediate gets forwarded to physical data centers or cloud-based systems. So there we have more powerful IT systems which can analyze, manage, and securely store the data. It takes longer to get results when you wait until the data reaches the stage 4. But you can execute more in-depth processing and analysis, as well as we can combine our sensor data with data from other sources to to get deeper insights. So the main difference between the cloud and the data center is that a data center refers to an on-premise hardware, while the cloud refers to off-premise computing. So this figure shows what we have talked so far. So there are things which collects analog data. So in stage 1, the sensors will measure the changes in the environment or some kind of difference in the objects which they are measuring the changes. So these analog signals will be passed into the next level, where we have the data acquisition systems which do the analog to digital conversion and also the data aggregation, and through the gateways we will pass it to the stage 3. And in the stage 3, we'll find the edge IT systems where we do the pre-processing and some sort of analytics. And if you need further analysis, then, and also if we need to store this data securely, we have to go for the stage 3, sorry, stage 4, where we find the cloud. So now let's see what is a reference model. The definition of a reference model is that it is a conceptual framework or blueprint for systems development. So in other words, it gives some kind of a framework that standardizes communication between heterogeneous or the different networks. It can be a layered architecture which defines the protocols, characteristics, and functions of each layer. The most commonly used reference model in IT systems is the OSI reference model. And OSI stands for the Open System Interconnection, and this was uh, developed by the International Organization for Standardization, or the ISO. Even though it sounds like iOS, we call it ISO. So there are 7 layers in this model. I think the final year students know about this since they learn the datacom subject in 3rd year, as I remember. So for a recap, we'll go through this model as well. So the bottommost layer, the physical layer, provides the physical medium where the bits are transmitted. And then we have the data link layer, which ensures the error-free transfer of data frames. And network layer is responsible for routing packets from source to destination. And the transport layer ensures the reliable message transfer without duplication of data. And next we have the session layer, which establishes, manages, and terminates sessions. And presentation layer responsible for translation, encryption, and compression. And finally, we have the application layer, which is the user interface, which provides the services to the end user. Similar to the OSI model, in the internet domain, we'll find the TCP/IP reference model. So here, instead of the 7 layers, we will see only 4 layers. The network access layer is doing functions similar to the functions of physical and data link layers of the OSI model, and transport and internet layers do the functions similar to the transport and network layer of OSI model. And finally, the application layer does the functions of application, presentation, and session layers of OSI reference model. And when it comes to IoT, there are several reference models which we can use in our researches as well. First one is the 3-layered model, and the next one is the 5-layered model. The 3-layered model defines the main idea of IoT, but it is not sufficient for research on IoT because research often focuses on finer aspects of Internet of Things. So that is why we do not see this 3-layered model in most of the IoT research papers, because we have to divide it into more layers to analyze further. So in the 3-layer model, the bottommost layer, the perception layer, is the physical layer, which has sensors for sensing and gathering information about the environment. It senses some physical parameters, or it is capable of identifying other smart objects in the environment. So the network layer is responsible for connecting to other smart things or network devices and servers. Its features are also used for transmitting and also processing sensor data. The application layer is responsible for delivering application-specific services to the end user. It defines various applications in which the Internet of Things can be deployed. For example, there can be applications in the domain of smart homes, smart cities, and smart health. If you look at the 5-layered model, the perception and application layers work similar to the 3-layer model. And we have 3 new layers: the transport layer, processing layer, and the business layer. The transport layer transfers the sensor data from the perception layer to the processing layer and vice versa through networks such as wired or wireless, which we discussed earlier under the WPAN to WWAN slide. So the processing layer is known as the middleware layer, and it stores, analyzes, and processes huge amount of data comes from the transport layer. It can manage and provide a diverse set of services to the lower layers. And also it employs many technologies such as databases and cloud computing and big data processing modules. And the business layer manages the whole IoT system, including applications, business, and profit models, and also the privacy of the user. And when you integrate the fog computing into the IoT, then there will be a different reference model. So a fog reference model presents a layered approach which inserts the monitoring, pre-processing, storage, and security layers in between the physical or the perception layer and the transport layer. So the monitoring layer will represent the functions such as monitoring power and also resources, responses, and services. The pre-processing layer performs filtering, processing, and analytics of sensor data. The storage layer provides storage functionalities such as data replication, distribution, and also storage. Finally, the security layer performs functions such as encryption and also decryption, and it also ensures the data integrity and privacy. And monitoring and pre-processing layers are done on the edge of the network before sending data to the cloud. So if you compare this model with the four-stage architecture, which we have discussed earlier, you will see that each layer performs some sort of functions related to one of the stages in that architecture. And I think you can do your own research in this area and come up with your own and more decomposed model which suits to your application as well. So from here, engineer Anuradha will discuss more on the reference models developed by the ITU, and over to you, Anuradha. You can continue from here.
Thanks, Rajiv, and I hope everyone can hear my voice.
Yes.
All right. Let me share my slides. Okay, I hope you can see the slides. Can you see the slides?
Yes, sir.
Yes.
All right. Okay, so thanks, Rajiv, for setting the stage so that I can, in fact, discuss these two models, which is one from ITU, the other one from the IoT World Forum. So we are basically going to discuss two models here. And I hope you all got a basic understanding of the importance of having the modular architecture, whether it is to do with the internet, which is the two models Rajiv mentioned. One is the ISO OSI stack, and the other one is the TCP/IP stack. Like they are, if I take those two as examples, but I really want to highlight the importance of sort of modularizing the whole stack so that you can have different layers and sort of have inter-layer communication defined by various standard protocols. So that is at very high level the importance of having a layered architecture so that your work, your studies, and certain experiments that you want to do is quite easy. Now, taking what Rajiv just mentioned to the next level and looking at these reference models in a more of a standard organization view. For example, if you take this view of ITU-T, this sort of encompasses what Rajiv mentioned in those reference models, which are sort of generic reference models compared to this one. But it essentially includes everything that he just mentioned, but in a different format if you want. So now in this one, you basically have 4 basic layers, starting from the very bottom device layer, going to the network layer, and service support and application support layer, and on the top, like the ISO-OSI stack, the application layer. Again, here, these different areas are referred to as layers, having the same meaning as the layers in the ISO-OSI stack. And covering all the layers, we have the management capabilities and the security capabilities. So they are not mentioned as layers. Of course, in the architecture itself or the reference model itself, there are sort of 2 pillars on the either side of the layers. They are mentioned as capabilities because they are sort of applicable to all the layers. For example, if you take security, security needs to be addressed at the device layers. I hope we discuss these things as we move on in the webinar series. But security is an important aspect, whether you are talking about your device layer, the network layer, or the application layer, or anything in between. Same for management. It's of no use if you can really sort of manage the devices, the components, whether the components are physical or virtual or logically defined or physically defined, irrespective of how you define and categorize or visualize your devices and the components, you need to sort of have some sort of management capabilities. So these security capabilities and management capabilities as per ITU-TIOT reference models are of 2 types, as you can see: generic security requirements or capabilities and specific management, generic security and specific security, generic management and specific management. So the reference model itself recognizes, or they actually understands the importance of looking at those 2 important capabilities, the security and management, both in the view of a generic viewpoint and also a specific viewpoint, right? So it allows us to sort of have not just one model fits all for something like that, but within the model itself, it allows you to have your specific security capabilities and specific management capabilities. And that is one of the good things of this architecture or the reference model. So if you look at each and every component, for example, IoT applications, I'm not going to discuss because we have a lot of applications, and I hope we discuss those things as we move on. But with regard to the service support and application layer support, which is the enabling layer for the applications to run, if you look at the generic support capabilities, they are the more common capabilities that we would find in any IoT platform or any IoT architecture. Things like data processing, data storage, as Rajiv also mentioned, like IoT, to a greater extent, IoT is more about the data, how you collect data, how you analyze data, and how you sort of get meaningful insights out of the data that you collect. So data processing and data storage is a generic capability. But if you look at the specific support capabilities, they include For example, as per the standard, particular capabilities which cater for the requirements of diversified applications. That again allows you to have like your own application and still that be covered as per the model. If you go one layer below, where you find the network layer, which is the supporting layer for all the capabilities that you identify in the service support or the application support layer. In other words, the network layer actually enables service support and application support. There also you find two capabilities, networking capabilities and transport capabilities. Networking capabilities include the control function of network connectivity, basically. That is what is meant by networking. And also access, transport, and resource control functions, not just providing the connectivity, but you need to sort of control your resources, mobility, etc. And also includes a very important aspect of how you authenticate, authorize, and account for the IoT devices, things, and IoT type of communications, layer type of capabilities. And when you look at the transport capabilities, they are more about not controlling, but rather providing the connectivity. So that includes, as I have highlighted, data information, control and management information. And layer below, which I'm going to discuss in a little more detail, is about the device layer, which includes device capabilities and gateway capabilities. So device capabilities, if you look at, includes these things, but they are not the only things that a device capabilities should address or would address, right? So these include direct interaction with the communication network. For example, how you gather and upload information directly without using gateway capabilities. The device itself has the capability of directly communicating. And indirect communication with communication network indirectly through a gateway, for example. You need to sort of, for example, have a private IoT network. You might connect all the IoT devices, or other IoT devices might communicate with the gateway. The gateway actually sort of aggregates, or maybe without aggregating, just pass the information on the upward direction. And there are certain environments where we find ad hoc networking, combination of both direct, indirect type of communication, and also sleep and wake up, especially needed in to save energy. Saving energy is saving power. For example, most of these IoT devices are actually running on their own energy resources. Like sometimes we have to, if you are an IoT device, you have to generate your own source of energy. For example, you are like that, so that you can source your energy. So that is about the device capabilities. And then you have gateway capabilities, which are, as the word mentions, gateway is something like that actually allows someone or something or a group to sort of find its way to a certain resource or certain location via this specific capability. So it could be wired or wireless technologies. For example, Rajiv mentioned few: Zigbee, Bluetooth, Wi-Fi, whether it is personal area, local area, it doesn't matter. You have many options these days, like you have your PSTN, 2G, 3G, LTE, Ethernet, DSL, etc. And then one of the other important aspects of gateway capability is the protocol conversion. Now, going forward, protocol conversion is one of the things, not only in IoT, but also in other domains of ICT and telecommunication, which is actually showing more importance in designing, for example. Because we have to deal with multiple protocols. Some are very, very well defined protocols coming out of standard developing organizations, some are not. So intercommunication between these multiple different protocols is also important. And sometimes you have to deal with like device layer protocols and device layer and network layer protocols. So that is one other capability of the gateway handle. And management I mentioned, but here from the standard, which is ITU-TIOT 2060, it basically covers these famous FCAPs, right? Those who are hearing it for the first time, FCAP stands for Fault Configuration Accounting, Performance and Security. In basically FCAPs you find in telecommunication field. Sometimes it is also referred in ICTs, but usually in telecoms you will find things related to faults, configuration, accounting, performance and security. And in the case of management, it is the management of all these things, for example, fault management. And again, as I mentioned, management capabilities handle two different areas: generic management capabilities, which are applicable to a generic definition of an IoT platform or IoT capability, and specific capabilities include the specific requirements. For example, the standard refer to something like a smart grid power transmission line monitoring requirement, which is not a generic management capability, but a very specific one. But generally you would find something like device management, local network topology management, traffic and congestion management, that you would find in any generic IoT architecture or a platform. Security also goes in the same lines in terms of the capability divisions, which is generic and specific, much similar to management capabilities as we discussed earlier. So there are also generic security capabilities include anything independent of the applications that you really don't care what is the IoT application, but you would say these things need to be included in general in a security point of view. For example, if you are talking about the application layer itself, things like AAA, authorization, authentication, and accounting, things like that. And then Rajiv also mentioned the importance of security, things like whether you are running an antivirus or how to protect of all these malicious attempts that we find anything connected to internet, be it your computer, be it your mobile phone, be it anything that we talk about in IoT. And the network layer, which is one of the dependencies for the IoT applications, because the network is the one actually sort of connects your devices, the sensors, actuators, etc., the hardware world to the software world and then to the user. So if the network layer is compromised, irrespective of, or rather, whether you have your application intact and devices intact, but you would not be able to get the full purpose out of your platform. And also at the device layer, not just the security that you need to address in the virtual world, the logical world, but also the security of the device, the physical security of the device itself is also very important. And there could be, for example, things like mobile payment. We need to look at different specific security capabilities, maybe not addressed within generic security capabilities. So this generic specific requirement is very important, especially when if you are doing a project or if you are sort of want to do an experiment. You need to always be careful, not just apply the available set of management capabilities. Maybe management would be okay, but security, you have to be very careful. Do not just apply what is defined in general. So I have AAA in place, I have antivirus, anti-spam, all these things in place, and don't think that your platform or the implementation is secure enough. So if depending on your application, depending on the specific IoT application, you have to go one step below and look at whether this requires any specific security requirement addressing. For example, if something involves mobile payment. That's about the IoT reference model defined by ITU-T, which is the telecommunication standards wing of International Telecommunications Union. The second much referenced and much referred reference model is this IoT World Forum reference model. But unfortunately, if you look at, or rather go and search what is IoT World Forum, there is no specific thing like that. And it has been something there in the past. Some say it is actually something driven by Cisco, but it's not like that. It is actually a collection of vendors and several other institutions who tried to sort of come out with this reference model. I think it's a coincidence that we have 7 layers here, which Rajiv mentioned. ISO OSI also has 7 layers, but they are not really coinciding with one another. For example, you really don't find things like presentation layer, transport layer, etc. But they are basically going from the edge where you are closer to the physical devices and the physical sensors, actuators, where you have the realities, if you will, like in the physical world, and then you go up the stack, and then you find the central or the centerpiece where you have more intelligence and the capabilities. You have capabilities and intelligence everywhere, but rather you, when I say you, it's being the human being, right, like us. So we are, for example, interacting more up in the stack than at the bottom. So as you go down, you will have more protocol-based, more standard ways of communication between devices, the edges, different data storage mechanism, data centers, the internet network, etc. But as you go up, it's more about the intelligence or the information that you really want out of all these different layers. So you have the physical device control layers, then you have connectivity, edge computing, data accumulation, data abstraction, application, and collaboration processes. So data abstraction is one of the important things Rajiv also mentioned in terms of aggregation and access. But if you really look at the information flows, it's important that you understand the layers, but I think it's more important for you to understand how the information flows. When I say information, it's not just the data directly associated with your IoT devices, the things. For example, if you are measuring temperature, humidity, not only that data. If you see the middle flow of data across different layers, the purple color, the arrow type of thing, it actually going from the very bottom hardware edge to your center, going across all the layers, right? But if you really look at the other two things, the control and policy information flow, the reference model considered, or rather considers the control, policy, and data also adds information flows, which I don't think is a problem, but control and policy is something that you take policy, you actually push policy from the intelligence level that you actually work with, you being the human being. Try to define your policies, try to define your intents. For example, what is really that I want to get out of this IoT platform or device. So something that I dictate my policies. So the policies will be communicated across the layers to the very bottom edge physical world. And also the controlling, I being the human being, I have the all the information that I need to control, not just the edge, but also the middle layers as well. So control and policy is something that I do from the top, or the central thing I push down, but data is something that actually going to and from upper layers and to the down layers. So these are the layers, quite similar to what ITU-T defines. And the two other aspects, security is actually shown in this architecture in a much awkward way, I would say. It is shown as a circle, but I think that the whole purpose of showing it that way is that security is something that you need to sort of think as a whole. So security is everywhere. Security is there in the layers. Security not there is in the layers, but security is an important aspect that you need to consider and apply if you are talking about the layers, in between layers, the protocols that you communicate in between layers, and also very importantly, the different information flows. If you take if I have an intent or a policy that I need to push that my IoT network or my sensors should work in this particular way, and I actually want to see that actually happens that way. I don't want anybody else to sort of intrude and change my policy so that my IoT device would behave in a different way than what I intend to. So those type of things. So security here also is an important aspect. And also management is also mentioned here, which means you really need to manage all these things as well. So if you look at this IoT World Forum Reference Model objectives, at middle level, somewhere around this real data storage and edge level, you have, if you want, you can sort of divide the 7 layers to IT and OT, the information technology and the operational technologies. So operational means it's the real operation of the network. For example, the above layers where it is more closer to you as the controller, you are basically doing the queries. You query the information base of the information system. Whereas the bottom layers, it is event based. Something happens, so it is how the data is generated. Or once collected, your data is basically at rest. So it's maybe in your storages, whether it is in the cloud, or as Rajiv mentioned, whether it is you're using fog computing, mist computing, edge computing, whatever. So your data is at rest. So it's collected data, let's say offline, for example. But whereas your bottom physical world, the operational technology world, your data is in motion. So you're sensing, you're collecting, you're passing data to the upper layers, you are getting information from the upper layers like your policies and control information. So data is always in motion. It could be your IT and OT work in real time, but more often you find that operational technologies are real time, because if it is a sensor, it has to sense the information or the data at that particular point of time. You cannot have like variations. But when you collect the data, your analysis and the way you treat data doesn't always have to be real time. So it could be non-real time as well. So these are some of the differences that we find in the IT and the OT. So if, for example, since we talked about two different reference models, one from ITU-T and the other one from the IoT World Forum, we can also try to sort of relate the two reference models. Now, if you really look at the physical devices and controllers that you find in the World Forum reference model is basically going or rather aligning with the device layer, which is in the ITU-T reference model. And the connectivity, which is basically the network layer aspects of the ITU-T model, is actually the connectivity layer 2 of the IoT reference models. For example, those who have done Cisco exams, you know, it is basically like how you usually see Cisco defines a router, their particular icon for a router and a switch, but irrespective of whether it is Cisco or something else, we basically have these connectivity devices, routers, switches, etc. And then you have your service support and application support layers and capabilities on the ITU side is actually represented by data abstraction, data accumulation, and edge computing to a certain extent on the IoT World Forum side. And then your applications are actually the application layer in the IoT World Forum reference. But on top of that, you have collaboration and processes, which involves people and business processes, which is not actually mentioned in the IoT reference model, but that is also very important aspect when you want to look at the more industry view of the IoT. So at this stage, you really understand that the IoT reference model defined by ITU-T is more of a kind of an, I would say, more of an academic type of reference model, whereas the IoT World Forum reference model is more of a industrial perspective type of a reference model. So they have considered not only the technical aspects of the IoT reference model, but also to a certain extent the whole business perspective and the other commercial perspectives as well. Apart from these two, you can also find this IEEE 2413 standard, which is the IoT architecture working group working on these things. So I could not find anything new to be defined by them, but they are a working committee. But that is something that you can always sort of track if you really want to see the progress of IoT standards. So to conclude the reference models, I would like to sort of highlight three important things. Like, we being engineers, we tend to always look at things in engineering perspective. Of course, you have these reference models, but this is often referred to as the engineering view or the plumbing view. The plumbing meaning that you're always looking at how one layer communicates with the other layer, and always doing data flow. So the information flows from bottom to up or top to bottom, something like that. So that is why these physical link network application layers are involved. So this is the kind of engineering view. The discussion so far is more about engineering view of the IoT reference model. But if you are really, of course, at some point of time, you have to sort of play the role of a designer as well. But a design view is more of an abstract view of the engineering view, where you really look at the point of view of an architect, for example. You are the fashion designer or something like that. Not really, but you have the design view. Basically, you're looking at your end customers, your end product, your end application, how the user experience is going to be, something like that. So you have the front end user touch points, how the user is going to consume or use this particular product or the solution. And then the back end admin touch points, for example, how the people who are controlling the whole architecture or the whole platform is going to handle that. And in between, a designer would simply think something like an enabling infrastructure. So the difference between the engineering view, which is more technical, more detailed, more about plumbing, which is your data flows, control flows, etc. The design view not necessarily look at things in the engineering view, but being an engineer, a design engineer, for example, you can have both the engineering view and the design view. Both are very important. They look at it's more of a user experience point of view, the front end, how it's going to be, the back end, how it's going to be, and what is the enabling infrastructure in between that could really glue the two endpoints. And going one step above or one step forward, engineering view, the design view, the next important view is the business view. What is the business objective or what is the business aspect of doing IoT, for example. So there you have these software-defined products, anything abstracted and defined or represented in software, for example, like your virtual machine. So virtual machine here is a kind of a metaphor for an example. You represent, or rather you emulate a physical computer in software. So that is what is meant by a virtual machine or a container or something like that. So that is a software-defined product. Then you have the hardware-defined product, your physical hardware thing. Then you are talking about the network fabric, different external and internal interfaces for your communication. So that is a different view altogether. So that is the last slide from my side today. I think just on time. I don't know whether you have. Yes, I'm sorry, I have taken more than 8 minutes more. But it is important. One of the things I want to really stress is that when you're doing not just IoT, but anything, that it's very important that you have not just the view of an engineer, but have the view of a designer and also have of a businessman for the business view, right? So with that, I conclude today's session. I think we can go for questions or anything that you guys have to clarify.
Yes, now it's time for the Q&A session. Feel free to type in your questions in the Zoom chat. And I would also like to mention that we have put up the link to the feedback form. Make sure to fill it today as well as in the coming weeks to receive the certificate of participation. And keep in mind, only those who fill the feedback form in all 5 sessions will receive this certificate. And make sure to provide the name you want in your certificate in block letters, preferably your full name.
Any questions? You can type the chat window. Last time we got like few questions over email, both myself and Rajiv. I think we have answered all the questions. Isn't it, Rajiv? No questions? So it look like we don't have any questions.
Yes, sir. Then shall we conclude the session for today?
But if anyone has like you get your questions after the session, you can, I think you have our email addresses. You can always send us those depending on the time we try to respond. And I think thanks, Isuri. I think you have shared with us the feedback for the last session and things that the students expect from us to cover. And I saw a long list. I don't think that we would be able to find time to discuss all these things in this particular webinar series, because it is all already set. I think Rajiv and myself, we actually wanted to share the load between us. Whenever it's possible to address those things here and there, we'll try to include those, but I cannot guarantee that we would be able to address all these topics. Some are directly relevant to IoT, some are not. In which case, we are more than happy to have another separate session or maybe multiple sessions to address those specific things under different umbrellas rather than trying to sort of include everything here in this IoT type of discussion.
Okay, sir. Then this marks the end of today's session. Thank you, Mr. Weragama and Mr. Udunuwara, for another valuable session. And we are waiting eagerly for your participation in the next sessions as well. Thank you everyone for joining us, and hope to see each and every one of you in the future sessions as well. Have a good night.
Thank you.